Alright, so now I'm just going to talk to you about partial pressures. Basically, this just refers to the pressure that individual types of gases exert when in a mixture of gases. So very simply, it's this, that if you have the total pressure of a mixture of gases, that pressure should equal the pressure exerted by one gas plus the pressure exerted by the second gas plus the pressure exerted by another gas, and so on. Well, if we look at some of the other relationships that we know, again, we know that according to our ideal gas equation, that the pressure total should equal the number of moles times RT over V. So we could also break this down into pieces, like the pressure total should equal N1 plus N2 plus N3, so on, multiplied by our ideal gas constant, temperature, and volume. So we can even simplify that even more. If we have the pressure of one gas, and we find that fraction of the pressure of one gas over the total pressure, it's going to be related to the same as the mole fraction of that gas over the total number of moles. So for instance, if in a container I had 1 mole of oxygen, 1 mole of H2, 1 mole of, let's say, CO2. So let's say the total pressure of that container was 3 atm. So if this is 3 atm for the total pressure, if I wanted to figure out, well, what's the pressure exerted by the oxygen? Well, the total number of moles inside that container, oxygen, hydrogen, and carbon, are 3 moles. And total, and I have 1 mole of oxygen. Well, the mole fraction is 1 to 3. So that ratio is going to be the same. So if I have 3 atm as my pressure, then that must mean that oxygen exerts a pressure of 1 atm. The hydrogen exerts a pressure of 1 atm. The carbon dioxide exerts a pressure of 1 atm. And you can just add those all up to figure out the total pressure. Or vice versa. If you know the total pressure, for instance, let's say you knew the total pressure was 3 atm, and you knew that hydrogen and carbon dioxide both exerted a pressure of 1 each, well, then you should just subtract, and you would get the pressure of oxygen. So that is how partial pressure is used. This also becomes important, for instance, when we are looking at something that is collected by bubbling up through water. One of the experiments that I have liked to do in the past is if I have a test tube inverted in a beaker full of water, in another beaker I might have hydrochloric acid and some magnesium. Fun lab, because then what I do is you end up generating some hydrogen gas. And so then what we like to do is bubble that hydrogen gas up into a test tube. So it will start bubbling up through here. So if you pull that inverted test tube once you've collected all your gas, and the test tube is pulled to a point And maybe I'll draw it in a different color so you can see. So this is the test tube. Let's say this is the water in the beaker, and if I pull the test tube to a point where the water in the beaker is exactly level with the water in the test tube, then the pressure inside my test tube should equal my atmospheric pressure, or the pressure in the classroom where I'm doing this experiment. So, however, this pressure in the test tube equals the pressure of the gas I was collecting. But one thing that you have to take into account is that water also, since we have water in here, sometimes some water particles escape from the whole liquid, and so that water vapor also exerts a pressure. So if you want to figure this out, and then maybe even use this to figure out and plug it into your PV equals nRT and figure out how many moles of gas you collected and so on, you would first have to find this water vapor pressure. And usually you can find that water vapor pressure in some table in your textbook somewhere. Or possibly even some other table online.